Okay, happy Monday. So today I just want to pick up where we left off at the end of that Friday video. And if you haven't had a chance to watch it yet, then that's okay, because we're basically just going to recap everything. But it's possible that it might not make sense because there's a lot going on. But okay, let's see here. So we were introducing hypothesis testing, but hypothesis testing using confidence intervals, which we're eventually going to move away from. But it's really important that we see that connection, that we can use confidence intervals to do hypothesis testing. So we're kind of introducing the concepts by way of example. And so the example that we're going to be kind of murdering here is, according to a 2012 Bank of Montreal RSP study of 1,000 Canadians 18 years of age or older, 67% of Canadians have a registered retirement savings plan, which is an RSP. A StatsCan study reported in 1999, which I guess is ages ago now, 57% of Canadians had an RRSP. And then I've added, is there evidence that the proportion of Canadian adults who have an RRSP has changed since 1999? Okay, so there's a lot of information here. And before we kind of dive in, there's the other way that we could word this type of question. So this is a one sample proportion question, which I'll put up here at the top. This is a one sample, because I'll talk about question types. So maybe I'll write that a little bit nicer. I'll talk a lot about question types because that's going to help you identify what you need to be doing. So once you've identified the type, and so far we've only seen one, this one, but we're going to start applying these techniques to other types of questions, and the techniques all stay the same, and that's what's nice. But it's a lot to keep track of, especially in the beginning. So then if you read a problem and you're able to identify what type of problem it is, then that kind of sets you on the path to how to solve it. So this is going to be a one sample proportion question. Why? Well, because we're talking about, we only have one sample of 1,000 Canadians 18 years of age or older, and 67% is a percentage, but we also know that all those three P's are all the same. So proportions, percentages are basically proportions. And I'm drawing a blank on the third P. Anyways, it'll come to me. But proportion and percentages, and probabilities, they're all the same, right? And so 67% is a proportion. And so this is a proportion question. And then you look to see how many proportions do I have? Well, I only have one sample proportion. So that's the type. Okay, so let's see here. Oh yeah, so the other way that we could word this problem before we get any further is this. So this question was worded using, or I should say giving's kind of a bad, it's not very proper, but it's okay. Giving n and p hat, right? So n was 1,000. We had a sample size of 1,000, and p hat was the 0.67, right? P hat is the sample proportion. So p hat is the 0.67. Okay. The question could have been worded giving n and x. Now x is what we're going to use to denote the number of successes typically. The number, and maybe I'll say in brackets, x equals the number of successes instead. So I'm just going to, let's see here. How can I'm just going to copy this little section here. So then I would say, oops. It would still give you your n, your sample size is 1,000, but instead of the proportion, it would give you 670 of those Canadians. I guess it already has of. And it's not very clean, is it? Put it above. Okay. So same type of question. It's just how is the information given to you? Okay. All right. So let's do a quick recap of hypothesis testing, and I'm going to kind of do a side-by-side. So we are introducing ideas using confidence intervals instead of what we call p-values later, but I do want to show you where those p-values would come in, so then you can see the connection. So just a quick recap of the steps for hypothesis testing. And usually I abbreviate hypothesis testing HT, but I should write it out once, I guess. Although people are usually pretty good at picking up on writing shortcuts. So just a quick recap here, because we haven't really talked about all of these steps except for the first step, which is to state the hypothesis. So the first step, and I break it up into 4 steps. I mean, there are some textbooks that kind of get down to the nitty-gritty and break it down into 7 steps, but I find that 4 is a nice kind of progression, and it gives you all the kind of clues that you need to move through the problem. So the first step is to state the null and alternative hypotheses, and alternative hypotheses. That's his hypotheses. Okay. And so in general, what we have is we have some null hypothesis H naught, and then we have some alternative hypothesis HA. Now, you're going to follow these up with colons because they're statements, right? And so often I'll see equal signs here, but that's not true. Equalities can really only be used for, in stats, we should really only use them for numerical equalities, right? And so these are statements, so you should use colons. Okay. And your hypothesis is always about the parameter, right? And so whatever the parameter is that you're interested in, okay, for example, in a one sample proportion question, we're interested in the population proportion, right? We use a sample proportion to try to learn about the population proportion. Okay, so in our case, we're going to be talking about P here, but later when we talk about the mean, then we would be interested in the population mean, right, which is mu. So that value is going to change, but in general, it's always going to be a parameter. Okay. And I find it simplifies things if I always have an equal sign in the null hypothesis. So sometimes if I don't know where to start, I'll just write out the equal sign. Yeah. And then here, this is going to be the hypothesized value. or the null value. Okay. Which in this case is going to be some p naught, so a p subscript 0. So that's the hypothesized value. That's the value that we want to compare our sample proportion to. Okay. Now what's nice is whatever you have here just goes down here in your alternative hypothesis. Okay. It wouldn't make sense to say, oh, I'm going to test if the population proportion is equal to 50% or 0.5. And then in your conclusion, oh yeah, well, I found that it wasn't 0.5. So so the mean is 4. That makes no sense, right? You have to talk about the same thing in both your hypotheses. And so on the other end here, the hypothesized value or the null value is also going to get transferred into your alternative hypothesis. Hypothesized value / null value, they're the same. Okay? The only thing that changes here is for now, we're going to have a not equal to here. So we introduce both the options, right? So either p is equal to some hypothesized value, or it's not equal to some hypothesized value, right? And so for now, right, if using confidence intervals to test the hypothesis, if using CI to test a hypothesis, our alternative hypothesis has to have the not equal to sign in it. If using a confidence interval to test the hypothesis, our alternative hypothesis, I use HA, but depending on what field you're in, I feel like biology might like H1 because they like the 0-1 situation, but it doesn't matter. They mean the same thing. It's just notation. So if you're using a confidence interval to test the hypothesis, our alternative hypothesis must be or must have the not equal to sign as the inequality. In general, we want to do our testing with the not equal to sign, and that's what we're going to call a two-sided test eventually. But I'm going to hold off on that for a little bit longer. We can test things like, oh, is the proportion less than some hypothesized proportion, or maybe it's more than some hypothesized proportion, right? But just to play it safe, we should use the not equal to sign, and that's a good default to have anyways. Okay, so you're going to state the null and alternative hypotheses, and what's really important, I'll make a note here, is that we do all our testing assuming the null hypothesis is true, right? And it's not until the very end where you say, okay, well, I assumed that the null hypothesis was true, but then I found so much evidence against it that then I can reject H0 in favor of the alternative hypothesis, which is typically the one we want to show. Okay? And so the note is that we do all our testing, so hypothesis testing, assuming H0 is true. Remember, H0 is the statement of no change. So it's where you have to start with your assumption and say, okay, well, I have to assume that the proportion of Canadian adults who have RRSPs now in 2012, right? I have to assume that that hasn't changed since 1999. And then I look at the numbers and I look at the spread and I look at what I would expect to see. And if I see a large enough difference, then I'm going to say, okay, well, that's evidence against that theory. And so then I can reject my null hypothesis in favor of the alternative. Okay, so we do all our testing assuming H naught is true, right? It's not until the very end. It's not until the end that we can reject H naught in favor of HA if we've found enough evidence against H naught. If we have found enough evidence against H naught. Okay. I am going to kind of call this the end of our review because that's kind of where we got to last day. Okay, but I am recapping the steps for hypothesis testing. So the next step is going to be step 2, which is going to be either building the confidence interval or doing the test if we're using a more formal approach. So step 2 is, I call it do the test. And that's really vague, especially right now when we haven't even seen anything. But doing the test is where we gather that evidence, that numerical evidence that we're going to use. Okay, and so if we built a confidence interval, or if we're using the confidence interval approach, then we're going to build the confidence interval. Builds the confidence interval. And the default is a 95% confidence interval. All right, but it'll say what type of, what confidence level to use. Okay. Or for later, if we're using the p-value approach, then we're going to calculate the test statistic. Calculate the test statistic. Now that sounds scary, but it won't be, because we've already calculated test statistics. For example, we're going to calculate a z-score. A z-score is a test statistic. We just haven't called it that before, right? But I'm going to save this for later. So if we kind of take it back, then, okay, if we're focusing on building a confidence interval, then we know how to do that, right? And so what do we do once we have a confidence interval? The third step is going to be kind of gathering evidence, right? So we did the calculations, and now we're going to use that to kind of put things together here. So I'll call the third step gather evidence, which in the confidence interval approach, this is where we compare that null value, the hypothesized value, to the confidence interval. Compare the hypothesized value, or hypothesized or null value, to the confidence interval from step 2. If you're doing a p-value approach, this is where you would find the p-value. the p-value approach, here you would find the p-value. Okay. So just comparing the hypothesized or the null value to the confidence interval, that's not really a step. We're actually going to talk about it in step 4. So that's why the confidence interval approach is a little bit easier, and that's why we start here. But in general, we should be using the p-value approach, and we will be using the p-value approach. But for now, in step 4, this is going to be our conclusion. Now, the conclusion, of course, depends on which approach you've been using. And so for the confidence interval approach, what are we going to do? We're going to have our hypothesized value, and I have my confidence interval. Now, if my hypothesized value is inside this interval, then I have no reason to think that that hypothesized value is wrong, right? It could apply to my population, so I don't have enough evidence to reject H0. Whereas if my confidence interval is outside of my hypothesized value, right, then I have enough evidence to say, okay, well, my confidence interval tells me that this parameter is either over here or over here, right, outside the null value. So then I have enough evidence to reject H0. So for the confidence interval approach, if the null value is inside the confidence interval or is contained in the interval, contained in the confidence interval, we do not have enough evidence to reject H0. We do not have enough evidence to reject H0. Okay. On the opposite side, right, if the null value is not contained in the confidence interval, then we have enough evidence to reject H0. Versus if the null value is not contained in the confidence interval, we have enough evidence to reject H0. And if you're going to reject a statement, then you should probably say in favor of what? And we only have one option, the alternative hypothesis, and that's usually what you're trying to show anyways. So then I add on in favor of the alternative hypothesis. So let's highlight the differences here. Right. If the null value is contained in the confidence interval, then we do not have enough evidence to reject H0. And if it is not contained in the confidence interval, we have enough evidence to reject H0 in favor of HA. If you're not rejecting H0, then you don't need to mention HA, because that just means that you weren't able to find enough evidence against the null hypothesis. It's really important that your conclusion is in terms of H0, because we did all our testing assuming the null hypothesis was true, right? And so you either have enough evidence to reject H0 or you do not have enough evidence to reject H0. And those are your only two options. Okay. The orange is better. So it is really important to state our conclusion in terms of H naught, since we assumed H naught was true, or we did all our testing assuming H naught is true. Since we did all our testing assuming H naught is true, right? So you only have two options here. You either have enough evidence to reject H naught, or you don't have enough evidence, do not have enough evidence to reject H naught. Those are your only options. Okay. And I know it's difficult as a student, but because you probably feel like, oh, well, I shouldn't be using her wording because that's, you know, I don't want to be caught copying or kind of sounding like I'm cheating. But in this scenario here, I want you to use the wording that I give you, because it's so easy to say the wrong thing and say something that's false. So in this case, you're going to use my wording, and you're all going to have pretty well the same wording, and that I'm fine with that. Okay. In fact, I encourage it. Okay. So, and then finally, our conclusion, you compare the null value in terms of, is it inside the confidence interval or not? And then your conclusion in terms of H naught. So do you have enough evidence to reject H naught or no? And then finally, you don't want to forget your conclusion in terms of the question, right? And so the conclusion will have three parts. And so the first part is in terms of the confidence interval approach. And I kind of want to parking lot the p-value approach for a little bit. I'll introduce it here because I guess it makes sense, but let's focus on the confidence interval approach. So the conclusion is going to have three parts. So first one is comparing the null value to the confidence interval. So that's where you're going to say, okay, either the null value is inside the interval or not, right? So you're going to articulate that. And it's always good if you can back up your statement with numbers, right? And I'll show you what I mean in our example. Okay, so you're going to compare the null value to the confidence interval, and then you're going to make a statement in terms of H naught. So the statement in terms of H naught, or maybe I should say conclusion in terms of H naught. Okay, do you have enough evidence to reject H naught or no? Now, of course, that's going to be linked to the first statement. So it is going to be kind of this daisy chain here. And then the third one, you don't want to forget, is your conclusion. Conclusion in terms of the question. That's the one people love to forget. Don't forget this step. Right, is actually answering the question. So what does my conclusion in terms of H naught, what does that mean in terms of the question? And that's the step that, you know, by the time you're all done, this huge question, this huge type of question, then you're so tired and you just want to be done, and then you forget this step, which is actually answering the question. And so you don't want to forget that. In terms of the p-value approach, and I'll just kind of highlight here more later. Probably not later today, later this week. So in terms of the p-value approach, your first step is to compare the p-value to the alpha level. So there's going to be some threshold, which is called the alpha level. So compare the p-value to the alpha level. Oops. Then you can state your conclusion in terms of H naught. And then once you have your conclusion in terms of H naught, then you can state your conclusion in terms of the question. So then you follow the same steps. And then I'm just going to cheat and copy this here, so that I don't have to write it again. Same as CI approach. So we don't know what this means. This is all gibberish, right? Comparing the p-value to the alpha level. Uh-oh, it's getting boggy, right? And I guess I should clean up. Compare the p-value to the alpha level. Now we don't know what those are, but it's going to be similar to comparing your null value to your confidence interval that we'll be doing. Okay, so kind of 4 steps, but the conclusion has 3 subparts, right? So there's a lot of steps here. And whatever you find helpful, right? If you find it helpful to break it down into 10 steps, then you could probably do that, right? State the null hypothesis, state the alternative hypothesis, and then find your confidence interval, and then compare the null value to the confidence interval. And then what does that mean in terms of the null hypothesis, and then your conclusion. I guess I can only get to 6, but I'm not very good into breaking into tiny parts. So that's it. You have to memorize these steps, but you don't really need to memorize them. You need to remember them, and the easiest way to do that is to memorize the steps in the beginning until they kind of feel like, oh, okay, now I need to do this, and now I need to do this, and so there is memorization here, but I mean, with enough practice, you'll get the hang of it. Okay. So let's see here. So let's go back to that, the question that we started with and kind of finished off the video from last day with, right? Where we were kind of introducing all the components of the question, and we've identified some key information here. So let me just grab this copy. So, put it on a fresh page here, and now, did I write Friday or today? Oh, it does say Friday. Thought for sure it said today when I pulled it down. Anyways. Okay. So we've done a lot of kind of important things already, right? So we have a sample from 2012, and that sample size is 1,000. So we have an N of 1,000. We're also identifying our population, so Canadians 18 years of age or older, which really we can just shorten to Canadian adults if we want to, right? That's fine. And then 67% of those 1,000, right? It's understood. So sometimes the wording can be a little bit difficult, right? But it's understood that this 67% is of those 1,000 Canadians. 67% of Canadians have an RRSP. And then we're told that a StatsCan study reported that in 1999, 57% of Canadians had an RRSP. So that's what's going to be our hypothesized value or our null value. And how we denote that is with a P0, and it's going to be 0.57. Okay, proportions, although we usually report them as percentages, in terms of math, we need to convert them back to proportions. So is there evidence? And as soon as I ask you, hey, is there evidence here? Then you have to do a hypothesis test, okay? That the proportion of Canadian adults who have an RSP has changed since 1999. And so here, I'm gonna follow this up with use a 95%, and maybe I should clean that up, use a 95% confidence interval to test the hypothesis. Okay, so that's what we're gonna do. The default is 95%. You can make a 90%, a 98%, whatever. Okay, so if we outline our steps, right? Our step 1 for our confidence interval approach, right? So this means that we're going to use, this is the confidence interval approach, which we are relatively comfortable with by now. So step 1 is to state our hypotheses. Now, step 1 is the same for the p-value approach and the confidence interval approach. So we'll always have to do this, is to state the hypotheses. Even if you don't know where to start, you can always set up your statements, right? And kind of see what happens. So H0 and then HA, there, I did something, right? Make sure you use colons. And then what I'm going to do is I am always going to use an equal sign in the null hypothesis. It's not until a little bit later where we could have some other options, but for now, I'm just always going to start with an equal sign. So I'm going to put that kind of in the center here. Then I'm going to ask myself, okay, do I have a proportion question or do I have a means question? If I have a proportion question, then the parameter that I'm interested in here is P, right? So then I know I have a proportion question, so I'm going to say that P is equal to, and this is where I put my null value, right? And so in this case, my null value is 0.57. Maybe I'll match that color here, or maybe not. 0.57. Okay. So this is going to be the null value from the question, which looked like P0 is 0.57. Okay. Now, once you have this P here and this 0.57 here, then you know what you have to do, right? We have to talk about P in our alternative hypothesis as well, right? And the only thing that's going to be different is the sign here. So I have to talk about P and how it relates to 0.57. And for a confidence interval, we use not equal to sign. use not equal to for the CI approach. And I'm going to follow this up with and as a default in general. So we've stated our hypotheses. Great. This is it. Okay, step 2 is to what did I call it? It's to build the confidence, do the test. I think I just want to call it do the test, even though that's more referring to the p-value approach. That's okay. So doing the test in this case means build the confidence interval. So from just looking at confidence intervals before in the previous section, right, we know that p hat plus minus. So if I want to build a confidence interval, then I take my sample proportion and I kind of add and subtract the margin of error. And so I need to find that margin of error. And so Z star times the square root of p hat q hat over n. And this is on that formula sheet that I've posted, but it's actually not updated. And so let's see here. Where is it? So it's in a different section, but that's okay. It's in the 6.1 section. And here, well, we've got all this here, but I'm just going to focus on this for now. I'm going to bump this over so I can have it beside here. Okay. So notice that it has the null and alternative hypotheses, right? And so this P naught is going to change depending on the question. That's the value you want to compare your sample to. Okay. And maybe I'll highlight that here. And so this is going to be the value you want to compare your sample to. Okay. That's important because it's hard to pick up on that value initially. Okay, so I've got the null and alternative hypotheses here, and in fact, you could probably figure out how to do the test for the p-value approach, but we're gonna parking lot that for a little bit, and we're just gonna build this confidence interval, but it's exactly what we have written out already, right? And so remember, Z star is the critical value at the confidence level that we want. Right, and then we're just reusing p hat, q hat is 1 minus p hat, and then n, and then square root it. Okay, so here, this becomes, so I'm building a confidence interval around my sample proportion, which is this 0.67, okay, and my n is 1,000. Okay, so let's just jot down 0.67. Q hat then is 1 minus 0.67. So let's figure out what that is. 1 minus 0.67 is 0.33. And we know is 1,000. And Z star, for a 95% confidence interval, you might remember it's 1.96, but I don't expect you to remember it. Although back in my day, we had to memorize them, right? But what do? Well, we can go to our Z table here. Just want to copy. Oh, I don't know what I went to there. Okay. Paste. And then I want to go back, grab the bottom section. Oh, gosh. All that, and I didn't actually grab it there. Gonna delete that, and there. Okay. So we kind of ignore everything here, and we're going to focus on these confidence levels and these Z stars. Now, if I go to a 95% confidence interval, which is what I am asking for here, or I made up that I am asking for, then 95% is here. So then my Z star is 1 point, oops. I guess I'm using this kind of light blue color from the table. And you can just jot down what it is, or you can even just say from the T table. Confusing because the T table has the Z stars in it, and we'll see why once we introduce the T distribution, but for now we can just call it the T table because that's what it is. Okay, so we've got 1.96, but notice how easy it would be if I asked for a 90% confidence interval. It would be 1.645. 98% confidence interval, 2.326, et cetera, right? And so it doesn't, the only thing that changes is the Z star, which is your critical value. Okay. So now I can fill this in, right? Copy. So I have all the components, and I have 0.67 plus minus 1.96, sure, 0 times 0.67 times 0.33 over 1,000. Don't forget to take that square root, right? And I already had 0.33 on my screen, so I'm going to take times 0.67, divide that by 1,000, and then take the square root of that. And then I'm gonna, usually I'll jot this down, but you don't have to, because sometimes it's just easier to run through the calculation all the way. But because I want you to be able to look back and understand the notes, I'm gonna jot it down here, but you don't have to. 0.01486943173. It's not until you've multiplied by 1.96 that you should jot that down for sure. 0.67 times 0.02914408619. This is what we call our margin of error. Right, the standard error was the 0.0 whatever, 0148 standard error. Okay. Especially for proportions, we should keep as many decimal places as we can for our margin of error, because it can be really small. And so I'm going to store this in on my calculator, and your calculator probably has a store function that I would recommend that you use, so you don't have to type out all those numbers all the time. But how do we report this interval? Well, I have to write it as with interval notation, right? So with rounded brackets separated by a comma, I write my lower value, comma, upper value. Okay, so 0.67 minus what I just stored puts me at 0.6408559138, comma, and then the upper value is 0.67 plus that value that I just stored, 0.6991440862. I'm not going to report these full values, right? But it's really important for checking your work or just kind of someone who's marking your work to see all those values to make sure that you did it correctly. And then we're going to round the values, of course. And so our 95% confidence interval is going to be 0.64. And maybe let's do, now, this is where it gets kind of sneaky. If we are reporting as a percentage, then I usually only go to 1 decimal place for the percentage. But for a proportion, I go to 4 decimal places, which is 1 more. Makes no sense. But there must be some reason I do that. But let's say 0.6409 up to 0.6991. Let's round to 4 decimal places, that's fine. Or 64.09% to 69.91%. If you want, you can. Especially if you're entering into a Moodle quiz though, then pay attention to whether it asks for the proportion or the percentage, because then those values are going to matter, right? Okay, so now we have our confidence interval. That wasn't so bad. We already knew how to do that. So now in step 3, we want to kind of gather evidence, which isn't really a real step in the confidence interval case, but what I'm going to do is I'm going to jot down a number line, and then I'm going to put my confidence interval on there. So my confidence interval is between 0.6409 up to 0.6991. So this is my 95% confidence interval. I think that it's the easiest way to visualize what's going on here, right? So for example, if my hypothesized value is somewhere in here, then that's just in line with the null hypothesis, right? It's not until my confidence interval says, okay, well, I'm 95% confident that this interval captures the true population proportion, right, in 2012. Well, is that the same as from 1999 or no, right? And so in this case here, I see that P naught of 0.57 is actually outside the interval, right? And so now that is what gives me that evidence against H naught, right? My null hypothesis is that 0.57 is somewhere in this interval, right? And then my alternative hypothesis is that it's not inside this interval, which is what we're seeing, right? So here we're just gathering evidence. Remember, a 95% confidence interval, we're only 95% confident because there's a 5% chance that we had this this weird sample that we're basing it off of, and this interval that we're seeing is just shifted off of the population proportion, and we don't know that, so that's why we're only 95% confident, because there's a 5% chance that we're wrong, right? So there's a 5% chance that you know, the interval might contain 0.57, and so that's why we just say we have enough evidence against H naught. We don't accept a hypothesis. Okay, we never accept a hypothesis. Okay, so gathering evidence. In my case, I find that it's easiest to look at the number line, or kind of a number line like this, and then I can really visualize whether it's inside or outside the interval. So then for step 4 is my conclusion. And this is where I write out what I'm seeing in step 3, right? So step 3 is later going to be finding the p-value, so actually calculating the p-value, and then we use that in our conclusion. But here we're just kind of visualizing, and here in the conclusion we can verbalize it. Okay, so since the null value of 0.57, or maybe I'll say of p naught equal to 0.57. So I always want to back up my statements with the numbers, all right? So since the null value of 0.57 is not contained in my 95% confidence interval from 0.6409 to 0.6991, right? We have enough evidence to reject H naught in favor of HA. We have enough evidence to reject H naught in favor of HA. And then most importantly, what does that mean in terms of the question? Well, the question was, and this is where you just reword the question as an answer. Is there evidence that the proportion of Canadian adults who have an RRSP has changed since 1999? Right? And so, yes, there is evidence that the proportion of Canadian adults who have an RRSP has changed since 1999. So there's nothing fancy here. You just reword the question as an answer. Therefore, there is evidence that the proportion of Canadian adults, I guess I should capitalize it, Canadian adults who have an RRSP has changed since 1999. So let's outline the different parts here. So here, since the null value of 0.57 is not contained in my 95% confidence interval, right? So that's the first part of our conclusion, which is comparing the null value to the confidence interval. Compare null value to the confidence interval. And then from that comparison, then you can say you either have enough evidence to reject H naught or no. So then here, right, we have enough evidence to reject H naught in favor of HA. So that part is your conclusion in terms of H naught. And then finally, your conclusion in terms of the question. Conclusion in terms of the question. Right? This is just rewording the question as an answer. reword the question as an answer. Okay. Good. So that's how you would solve it using a confidence interval approach, which is kind of the becoming more standard. There are a couple of problems with the confidence interval approach, and that's why we typically rely on hypothesis testing, especially if you are trying to publish in journals and just anything in academia. You're going to need to use p-values and the p-value approach, because it's still considered kind of the standard hypothesis testing approach. But more and more people are coming around to using confidence intervals instead. Okay. So that's kind of the end of the question here. So just do a little tilde or a little twiddle, let's call it, because I don't know what it's called. So there are some not drawbacks, but just kind of some shortcomings of using the confidence interval approach. So there are some shortcomings of using the confidence interval approach to testing a hypothesis. The first one is that we are only able to talk about a change. Okay, so the first one is that we can only establish whether there has been a change, whether there has been a change from the null value. Okay, that is the alternative hypothesis, or sorry, let's start. H naught is that P is equal to some P naught, and the alternative hypothesis is that P is not equal to some P naught. Okay, so that's where this change comes from, right? Is it not equal to this P naught? Clean that up. Okay, so this is what we call a two-sided test. And maybe the whole thing is in quotes. Versus an alternative hypothesis that P is less than P naught, or an alternative hypothesis that P is greater than P naught. This is what we call a one-sided test, which requires p-value approach. Requires the p-value approach. Okay. So we can really only talk about a change. Now, it doesn't actually give us how different from the null value it is, right? So it doesn't quantify how different the sample is from the null value. Doesn't quantify how different the sample is from the null value. Okay. So all we were able to say is that 0.57 wasn't in that interval, but we don't we're not able to say, oh, this interval was this far away from 0.57, because it's not going to be linear like that, because we've got this normal distribution, right? And so when we're talking about probabilities, if we're in the center, then the probabilities are higher than they are out in the tail, right? And so those probabilities change. Right? We don't have this uniform distribution anymore, and so it makes it harder to quantify. Right, so it doesn't actually tell us how extreme that value is. Okay, so this would require, right, requires the p-value approach. Okay. And the last one, which is kind of important, especially if you're staying in academia, is in terms of publishing papers and any sort of academic publications require the p-value approach. Okay, so academic publications. I'm going to say will likely require the p-value approach, only because there has been a lot of discussion kind of recently saying, okay, well, maybe we shouldn't be relying so much on p-values. Maybe a confidence interval is kind of enough. Okay, but academic publications will likely require the p-value approach. Okay, so the formal hypothesis testing approach is using the p-value. Okay, so formal hypothesis tests require the p-value approach. Now, where I want to end today is just introducing what the p-value is and what it looks like. Okay, because this is kind of this mystical thing that we don't really wrap our heads around until maybe even, you know, you're studying for your final exam, and that's when it happened for me. So I didn't understand these things. I just kind of had them memorized, and I knew when to use them, and I knew what to do, but I didn't truly understand the concept of p-values until I was studying for my final exam. And I had this kind of moment going, oh, well, of course that's what it is, right? And so, but I mean, I look forward to you having that eureka moment as well. But until then, just kind of stick with it and stick with the steps that we've outlined and just kind of work through it methodically until one day it's going to kind of, it makes sense. So the p-value is a probability. Okay, and it's the probability of seeing something as extreme or more extreme than what you saw. Okay, so it's the probability of seeing something as extreme, oops, or more extreme than what you saw in your sample, in your sample, assuming the null hypothesis is true. Assuming H naught, and maybe I should write out the null hypothesis, assuming the null hypothesis is true. Okay. So, for example, okay, what we did was we said, okay, we had our null hypothesized value was 0.57, and we had a sample proportion of 0.6 something, 0.67. Were they both 7s, ending in 7? No imagination for me. Okay, well, all right, that's okay. So 0.67. So if we want to find a probability, the probability of seeing something as extreme or more extreme, assuming the null hypothesis is true. Well, assuming the null hypothesis is true, then we can say, assuming we've checked all those conditions, which we should be doing, but we're introducing a lot of stuff here. So I kind of parking a lot of the conditions. And so assuming conditions have been checked, right? Then we can use this normal distribution centered on P. So the hypothesized proportion, 0.57, we assume the null hypothesis is true. So that means it's going to be centered on the null value. Then what we do is we take our P hat, right? And we say, okay, well, this is what I saw in my sample. So that's going to go over here. Remember, this is just the number line here. So I saw 0.67. Okay. The probabilities are just areas under the curve, right? And so the probability of seeing something as extreme or more extreme, that's what puts me in the tail, than what you saw in your sample, assuming the null hypothesis is true. And so this area here becomes our one-sided p-value. Now, to make it match a confidence interval, remember we said we had a two-sided p-value. So then you kind of just imagine it happening on the other tail as well. So this is our one-sided p-value. Okay. And to find the two-sided p-value, we multiply the one-sided p-value by 2 to replicate the area in the other tail. Okay. So I'm going to change it to be kind of a more dotted one. But so basically what happens here is you kind of replicate it as happening in the other tail as well. Okay. What we did with our confidence interval was we built a confidence interval around the sample proportion, and then we found the 95% of the curve around that sample proportion, right? But that's kind of a lot to wrap your head around. So I think that's where a good spot to kind of end it today. I see I have an extra dot there. I don't need that. Change my pen back. But try, oh, last thing I wanted to say, right? How do I find these areas? Well, I need to find a z-score, which I can use if I have a normal distribution. And we've already seen it on that formula sheet that I posted, that you can calculate it. So just to try it out, you could try going through this hypothesis test with the p-value approach with just what we've talked about, but we'll go through it together next day. I'll stop the recording here. If you have any questions, let me know. Otherwise,